Hello everyone, today we are going to study the general result for eigenvalue and eigenvectors 7.2. So firstly, have a quick review of eigenvalue, eigenvectors. Okay. So for the eigenvalue, we calculate a minus lambda I and we make the determinant equal 0. We get a polynomial in terms of lambda and then we solve for lambda and solve for lambda. Okay, eigenvalues. And then for eigenvector, we plug lambda I. Sometimes we may get several lambda. So we plug in lambda into A minus lambda I. Solve this. Solve for V. Okay. That's the eigenvector, right? So we can, by using those steps, we can find eigenvalue, eigenvector. And now let's take a look at the definition 1. Sometimes in the last class, we noticed for the polynomial, we may have, let's see, the polynomial if we get something like lambda minus 2 squared, lambda plus 3. So you can see the lambda equals 2 repeated twice, right? So let's see, definition 1. I'm just going to give you example here. So that means P lambda means the polynomial, characteristic polynomial. If our characteristic polynomial look like this, lambda minus 2 and lambda plus 3 cube, and then we set this equal 0, and the power is called multiplicity of lambda I. The power is called of lambda I. Let's take a look at for lambda. For this example here, lambda equals 1. What's the multiplicity? The power has 2. So we set m equals to 2. M is multiplicity, okay? And then for lambda equals to 2, m equals 1. For lambda equals negative 3, right? And multiplicity, this one has power 3, so equals 3. It's pretty easy. Now let's take a look at definition 2. We have a matrix. So for the given eigenvalue lambda I, okay, so let's see. For a given lambda I, we write down EI. Denote the set of all corresponding eigenvectors. Set of all vectors V satisfying AV equals lambda IV. So actually it just means corresponding eigenvector. Then EI is called eigenspace. If we put all eigenvectors together, it's called eigenspace. Of A corresponding to that lambda I, corresponding to lambda I, okay? Now let's take a look at example 1. I will show you how to find the eigenspace for a given eigenvalue. Let's see. Determine all eigenspace for this matrix. A is given by 2 by 2 matrix. So 5, negative 4, 8, 97. Let's take a look at this one. And now we can also review how to calculate eigenvalue. First step, set determinant a minus lambda I. So this means 5 minus lambda, then 7 minus lambda, and negative 4 and 8. Simplify. So 5 minus lambda, negative 7 minus lambda, and plus 32 equals 0. Simplify this one, and after simplify, we skip the detailed calculation here. We just expand and then factor this out. Okay, so lambda, we get two eigenvalues, which is negative 3 and 1. Okay, so we get two eigenvectors. Now let's find the eigenvectors corresponding to each eigenvalue. So now let's see. For lambda equals negative 3, we plug into a minus lambda I. Let's see. So it's going to be 8, negative 4. 8, negative 4. We did this in the last class, actually same example. So we are going to do this a little bit quicker. So this is 1, negative 1/2, and the second row will be all zeros, right? Let's write down the eigenvector, okay? So the eigenvector should be, the second word should be free variable. So should be, we can make a R, T, S, whatever you like. So I'm going to make a R. And V1 should be positive 1/2 R. Okay, and if we factor the R out, it's going to be 1/2 1. So let's write down, this is the eigenvector. Right now, everything is same as before. Now let's see how to write down eigenspace. So eigenspace, we just write down this one, E1. Okay, E1. We write down this in set notation because this is a subspace. The vector, so you can see all the eigenvectors, they are in R2 because it has two components. Okay, and all the vector has this form, 1/2 1, and R is free variable, so R can be anything, just like this. Set notation for the eigenvector. Let's try another one. For lambda equals 1, we plug into a minus lambda I, which is 4, negative 4, and 8, negative 8. Change this into row echelon, 1, negative 1, 0, 0. And the second component should be free variable. So the vector should be, let's see, it should be t here. And the first component should be positive t. Right, positive, because it's when we move to the right side, it's become positive. Factor the t out, 1, 1. Let's write down the eigenspace. E2 equals 2. The vector belongs to R square, and all the vector has this form, and the t is free. Just like this. Okay, eigenspace. Now let's take a look at example 2. Determine all eigenspace and their dimensions for the matrix. Okay. All eigenspace and their dimension. Do you still remember what the dimension means? That means the number of the bases, right, in a space for the matrix. This matrix is 3 by 3 matrix. 3, negative 1, 0, 0, 2, 0, negative 1, 1, 2. Okay, so let's see. First step, definitely we need to find eigenvalue. 3 minus lambda, 2 minus lambda, 2 minus lambda, and here negative 1, 0, 0, 0, negative 1, 1. We did this before, actually, same thing. We use the last column to expand, and actually we get this one. Okay, so we find lambda equals to 2 and lambda equals 3, but for the lambda equals to 2, we have the multiplicity 2, because for that lambda, let's combine this 2 minus lambda actually square, right? So by definition 1, the multiplicity is 2. Let's see, for lambda equals 2, a minus lambda I, which is this one, 191, 0, 0, 0, 0, 91, 1, 0. After we reduce into row echelon, the third row should be all zeros, so we have two free variables, second component, third component. So our vector equals to S and T here for number 3, number 2 components, and V1 equals 2. If you look at the first row and look at this position, when we move to the right side, positive S. Okay, positive S. And do you still remember how to separate this into this way? S times 1, 1, 0, T times 0, 0, 1. Right. Now let's write down the eigenspace. All the vector belongs to R3, right? And all the vector can be written as this linear combination. Actually, that means those two vectors actually disband the eigenspace. And ST belongs to R. They are free variable. So the dimension of the E1, you can see there are two vectors, and we can easily prove they are independent. Okay, independent. So this dimension is 2. So it's interesting, dimension equals to the multiplicity of this eigenvalue. Now for lambda equals 3, a minus lambda I equals 2. Because we did this before, so we just do this a little bit quicker. 181, 1, 0, because we need a leading 1, so we switch this into here, and 0, 1, 0, not 0 here, okay, and 0, 0, 0, only one free variable. Let's see, one free variable, that means one, two, three. Okay, the last one we can say R. So the V2 should be 0. How about V1? V1 should be negative R, right? Okay, when we take the R out, so negative 1, 0, 1. Eigenspace E2. V belongs to R3. All the vector has this form, negative 1, 0, 1, and R is free. And what's the dimension? Dimension of the E2 is 1, because there's only one vector. It's kind of like a basis. Okay, the basis is this vector, negative 1, 0, 1. Let's see, there is one theorem. Okay, theorem 1 says eigenvectors corresponding to distinct eigenvalues are linearly independent. Eigenvectors corresponding to different distinct, same as different eigenvalues are independent. So we skip the proof. Okay, this is just this one. Now let's take a look at definition 3. Definition 3 is for some matrices. It's called defective or non-defective? Let's take a look. A matrix A that has n linearly independent eigenvectors is called non-defective. I will show you an example. What's the meaning? It's pretty easy to understand. Okay, if A has less than, or we can just say otherwise, is called defective. Let's take a look at our example 2. Example 2, we have, for the matrix, we have, let's see, we have 2 eigenvalues, right? And we have 3 actually eigenvectors, okay? Let's see, I'm going to box them. Here we have one vector, we have one vector, they are independent, and they are also independent to this vector. So for this matrix, that is 3 by 3, and here we have 3 vectors, independent vectors. So for this one, that is non-defective. Okay, defective. I'm going to show you example in the example what a defective matrix look like. Let's see. If we have a matrix 1, 1, 0, 1, okay, after we solve this, so you can see A minus lambda I for this one should be 1 minus lambda, 1 minus lambda, 1, 0, and this is pretty easy to solve, right? So lambda equals 1 with multiplicity equals 2, and we plug in 1 into this matrix. So it becomes 1 minus 1, 0, 1, 0, 0. Change this into row echelon, and this is already a row echelon, right? And in this case, do you still remember how to set free variable? Who is the free variable? Who has no leading one is the free variable, so it should be V1. Because second position has leading one here. So V vector should be S, and this equals to, if we look at the first row, it's like 0 plus V2 equals 0, right? So V2 is 0, which is S10. In this case, you can see we only get one eigenvector, but even our multiplicity is 2, okay? We get one eigenvector, and this matrix is 2 by 2. So in this case, our A is defective. So A is defective. Okay. And the same thing. Let's try one more example. A is this one, 4, -1, 1, 2. We want to see whether this matrix is defective or not. Same thing, find eigenvalue and then find the eigenvectors and see how many independent eigenvectors we have here. If we have 2, non-defective. If we have 1, so defective. Let's see, A minus lambda I. We did this so many times, right? -1, 1. Okay, simplify. 4 minus lambda, 2 minus lambda, and then minus -1, so plus 1. Simplify. Lambda minus 4, lambda minus 2, plus 1. Lambda square minus 6 lambda plus 8 plus 1. So which lambda square minus 6 lambda plus 9. Factor this out, equals 0. So we get one eigenvalue, lambda equals 3 with multiplicity equals 2. And definitely we only have one eigenvalue. We plug in this. And 4 minus 3 should be 1, 91, 1. 2 minus 3, 91. Reduce this into row echelon. 1, 91, 0, 0. We have free variable. Who has no leading one is the free. So v vector should be, okay. Let's write down detail. You can factor s directly in the future. Second component is s. First component should be positive s. So when we factor s out, 1, 1. So we only get one eigenvector. But our A is 2 by 2, so n is 2. When we have a less number of the eigenvector, then the number, then the n, then we say A is defective. Let's see. Can we try one exercise problem? Because I think it's pretty good problem. Yes, reviewed a lot of things. By doing this one, we can review like how to solve linear system. Okay, you can determine this is defective or non-defective. I'm going to give you the solution. Very easy to solve for lambda 3 m equals 2, and plug in a minus lambda I 0, 0, 0, 0. Interesting, right? So what's the meaning of that one? Means both components are free variable. v1, v2 both are free. So in this case, the vector can be s and t, just s and t. And we don't write down this way, we write down into this way, right? Because we want to find the number of the independent vectors. So we write down 1, 0, 0, 1. So how many vectors we have here? 1, 2, same as the number 2. So this is non-defective. Okay, that's the meaning of defective or non-defective. Let's see, we have a theorem. If we have a matrix A, and this matrix has n distinct eigenvalues, then it is non-defective. What's the meaning of this one? I'm going to show you. For example, it's like if for a given matrix A, if the p lambda equals to, this is 3 by 3 matrix, okay? And after, if this polynomial equals this one, lambda plus 2 or just times lambda plus 3 equals 0, like this one, and we know this this matrix has 3 distinct eigenvalues, -2 and then lambda 3 equals -3, right? So same as number n, okay? So that means has n distinct eigenvalues. This is the example like this. And then it is non-defective because we have a theorem 1. Theorem 1 says what? Corresponding to distinct eigenvalues, the eigenvectors are independent. So we can find like a v1, v2, v3 corresponding to those 3 eigenvalues, and by using the theorem 1, they are independent. So we have exactly the same number as the n independent eigenvectors, so it's not defective. That's why, okay? And then we have another theorem, 3. Matrix A is non-defective if and only if I'm just going to write down this one. Dimension of EI equals MI. So what's the meaning? That means the dimension of each eigenspace is same as the multiplication. For example, if P lambda equals to lambda minus 2, so first example, lambda plus minus 3, okay, if I remember correctly. So like this one, and A is 3 by 3 matrix, okay? And for this is example 1 at the beginning of the class, and the lambda equals 2, and the multiplicity is also 2, and the lambda equals 3, multiplicity equals 1. Okay, so what's the meaning of this theorem? This means dimension of the eigenspace. So if we look at this one, the eigenspace E1 equals to R3, and the vector equals like R something plus T something, okay? And we noticed this eigenspace has dimension 2, right? Because we have 2 vectors, and this is same as, so dimension of the E1 is 2, and the same as the multiplicity also is 2. In this case, we have 2 independent eigenvectors. And for the other eigenvector, because this is also independent, they are all independent, so that means when we add all those independent eigenvectors together, we have exactly number n eigenvectors. So that's why we have this theorem. In the future, how to tell the matrix defective, non-defective? So we can also use this theorem. Summary. Okay. What's the meaning of multiplicity of lambda I? That means the power, right? Power of the eigenvalue. And how to find the eigenspace? It's just a set notation for this is example. Okay. For example, let's just write down this randomly. Doesn't matter too much here, so something like this. And ST belongs to R. This just set notation of all the eigenvectors. And number 3, determine a given matrix is defective or non-defective. There are several ways. If A has n distinct, like A has n distinct eigenvalues, non-defective, right? Okay, if the dimension of the EI is same as the multiplication corresponding to that eigenvalue, then it is also non-defective. When it's defective, when the number of the independent eigenvectors, number of the eigenvectors smaller than number n is defective. Okay, just those 3 things you need to know. We can stop here.